On this video, we will talk about the sine and cosine ratio. But before we talk about the sine and cosine ratio, let's just refresh what the tangent ratio is. But recall that from our previous class, we said that the tangent of any angle that will always be equivalent to the opposite side divided by the adjacent side. Well, let's take a look at the triangle right here on the right hand side. Let's find the tangent of B and let's see if we can come up with a conclusion. So if we want to find out the tangent of B, first we indicate where B is located at. So here is my B. And let's just label our triangle based on this angle. So if this is my angle of reference, then therefore AC is my opposite. Notice that here we have a right angle, so therefore what is opposite to it is the hypotenuse, and by order of elimination, this must be my adjacent. So if we want to find the tangent of B, that has been defined as the opposite over the adjacent. But notice what the opposite is. The opposite is AC, and the adjacent is AB. Is it possible for us to find out an actual numerical representation for the tangent of B? Well, let's take a look at this triangle here. It's an isosceles right triangle because we have 45, 45, and 90. So therefore, this side, the side AB, must be congruent to the side of AC. So in any isosceles triangle, or any right isosceles triangle, or a 45, 45, 90-degree triangle, notice that AC will be the same measurement as AB. So therefore, AC over AB, that's equivalent to 1. So therefore, the tangent of B is just 1. And this will always be a statement that we can use whenever we want to find out the tangent of either B or C when it comes to a 45, 45, 90 triangle. So with that same statement, then the tangent of C, it's also the tangent of C, it will also be equivalent to just 1. So this was just a quick refresh of what we discussed previously. But let's talk about our two new ratios, the sine and the cosine. And again, everything that we've been discussing regarding tangent and now sine and cosine, they all have to do with right triangles. So that's the only condition. The only condition is that we have right triangles. So for any right triangle, then the following ratios can be defined. And we call those ratios the sine and the cosine. So let's start by just defining what the sine and the cosine is. In order for us to find a sine and a cosine, we need a reference angle. So let's assume that A is my reference angle. So if A is my reference angle, then this side is the opposite leg. This is my right angle, so therefore this is my hypotenuse, and therefore by order of elimination, that's my adjacent. The way that we're going to be defining the sine of an angle, that will always be equivalent to the opposite over the hypotenuse. So if we want to find the sine of angle A, we're going to get the opposite leg and we're going to divide it by the hypotenuse. So that's how we're going to be defining the sine. Sine is opposite over hypotenuse. Now for cosine, it will be equivalent to the adjacent over the hypotenuse. So notice how we have three different ratios. We got tangent, which is defined as opposite over adjacent. And now we're introducing two new ratios. So the sine of an angle, that will always be equivalent to the opposite over the hypotenuse, and the cosine of an angle, that will always be defined as the adjacent over the hypotenuse. So these are just definitions that we're going to be using throughout the lesson. And let's just summarize it. Let's summarize the three different ratios that we have discussed. So the tangent of any angle, that is always equivalent to the opposite over the adjacent. So as a matter of fact, I want to start with sine. So the sine of an angle, that's equivalent to the opposite over the hypotenuse. And we just stated that the cosine of an angle, that is equivalent to the adjacent over the hypotenuse. And also, on our previous lesson, we stated that the tangent is opposite over adjacent. So these are just ratios that we have to memorize. There are three ratios: sine, cosine, and tangent. But we do have a small way to kind of remember how it's been defined. And for that, we're going to use this little phrase right here. So, as a matter of fact, I'm just going to write it like this. So, katoa. Sokatoa. So this is what we're going to be. This is just a small phrase that we use that can help us out remember the actual ratio for those functions. So notice that the first three letters is spelled SOH, which is so. This is one way of remembering that the sine is equal to the opposite over the hypotenuse, which is how we have defined the sine ratio. Ka, CAH, this can be seen as the cosine being equivalent to the adjacent over the hypotenuse, which is what we do have here. And TOA, they can help us out to remember that the tangent function is equivalent to the opposite over the adjacent. So SOHCAHTOA is just a small acronym that we can use that can help us out remember the ratios for either the sine, the cosine, and the tangent function. So this is going to come in handy. Let's actually use the ratios now. So find the value of x and y to the nearest integer. Let's see, what do we have? So here notice that we have a reference angle, which in this case is 65, 67. And now x, if this is 67 is going to be my reference angle, then x can be seen as my opposite. 120 can be seen as my hypotenuse. And this y can be seen as my adjacent. So now we want to find the x and the y value. But let's think about this for a second. We have a reference angle, we have the hypotenuse, and we want to find out the opposite and the adjacent. But notice that the sine of an angle, that's equivalent to the opposite over the hypotenuse. But let's see what happens if we find the sine of angle 67. So if we take the sine of 67, that's going to be equivalent to the opposite, which in this case is x, divided by the hypotenuse, which in this case is 120. And notice that we can use this equation now to solve for the value of x. Because now if we multiply 120 to both sides, 120 will cancel out. And now we have an expression for x, because now x is equivalent to 120 times the sine of 67. And how can we find out the value of this? Well, for that, we have a graphing calculator here. So let's use a graphing calculator to define this. And again, when you're using your graphing calculators and you're dealing with degrees, because notice that this angle is given to you in degrees, we definitely want to make sure that calculus is in degree mode. So we go to mode, and now we can see that it's in degree. So mode degree. Now that it's in degree mode, let's actually plug in the value. So 120 times the sine of 67. So in this case, x will have a value of 110 point, let's keep it to the nearest 10, 110.5. So notice that we know what x stands for. X stands for 110.5. So now we want to find the y. But notice that y is the adjacent. So let's think about a ratio that uses the hypotenuse and the adjacent, because since I have an angle, I have the hypotenuse and I need the adjacent. So notice that can be given to us by cosine, because cosine is being defined by the adjacent or the hypotenuse. This is what we want, and this is what we have. So let's just set that up. Let me use a different color so we don't get a mix with the sine. So now for cosine, recall that cosine of an angle is equivalent to the adjacent over the hypotenuse. But let's plug in what we know. So therefore, if I take the cosine of this reference angle, which is 67, that's equivalent to the adjacent of 67, which is y, over the hypotenuse of 67, which is 120. And notice that we can use the same strategy as we did previously to find the value of y. Because now, if we come back to here and we multiply 120 one more time, notice that this 120 will cancel out with this 120. And what we're going to have left is going to be 120. It's going to be y equals 120 times the cosine of 67. And therefore, we can use a graphic calculator to find this. So now, let's find the value of this. So that would be, let me clear this. So 120 times the cosine of 67. Now we can see that y has a value of 46.9. Let's keep it to the nearest 10. So therefore, y has a value of 46.9 degrees. I'm sorry, not degrees, but just length. It can be centimeters or meters. So let's do one more example. Let's do one more example here. Let me just create a small divider here. So now, how is the initial problem here different than what we do have on the right-hand side? Well, under example A, we were looking for the lengths of the sides. But now notice that in example 2, we're looking for an actual angle. Well, what strategy can we use to find the measurement of that angle? Well, let's label our triangle. So we want to find out angle N. And what do we know about this triangle with angle N? Well, we know that 22 can be seen as the opposite, and 40 can be seen as my hypotenuse. But now let's think about this for a second. I have three different ratios that I can use. Now, which of these three ratios uses opposite and hypotenuse? Because I want the angle, but I know the opposite and I know the hypotenuse. Notice that we could use the sine function, because if we wanted to use cosine, we need the value of the adjacent, which we don't have it, which we can find it using the Pythagorean theorem because it's a right triangle, but that's extra work that we don't need. And notice that we cannot use the tangent because the tangent uses opposite and adjacent. And again, we don't have the adjacent value. And again, we can find it using the Pythagorean theorem, but that's just extra work that is not needed. So we're going to be using the sine function, because the sine function is being defined as opposite over hypotenuse. And notice that those are the values that we do have. So let's set this up. This is saying that if I take the sine of this angle N, that's going to be equivalent to the opposite of N, which in this case is 22, over the hypotenuse of N, which is 40. Let me just rewrite that because that looks like a 90. So this is the setup. So we're pretty much almost done because we have the setup. This is the most complicated part. Now, to properly solve for N, as a matter of fact, I'm just going to rewrite it here on the middle. So this is 22 over 40. And again, we want to solve for N. In other words, we got to get rid of the sine. And just like we did yesterday with the tangent function, we could have also done the same with the sine function. So if I want to cancel out the sine, I need to multiply what we call the inverse function. So the inverse of sine on the left times the inverse of sine on the right. And that way, the inverse will cancel out. And now I have that N is equivalent to the inverse of sine evaluated at 22 over 40. And this is something that we can use our graphing calculator. Let's actually use our graphing calculator. So here we have it. Oh, where is it? It's over here. So let's actually find the inverse of sine at 22 over 44. And again, make sure that your calculator, it's in degree mode. To find the inverse of sine, you're going to see here in sine, and on top of it is a little yellow. It says sine inverse. So we're going to press second sine 22 over 40. And we press enter. Notice that this gives us a value that N is approximately 33.4 degrees. So this is one way that we can use the sine and the cosine ratios to define either lengths or angles in any right triangle.